Picture this: a single second, one heartbeat, a snap of your fingers. In the grand scheme of things, it's nothing. A blink so fast you'd barely notice it. But rewind the clock 13.8 billion years, and that same fleeting moment becomes the most important second in history. The first second of the universe's existence wasn't just the beginning of time, it was the birth of everything. Every star, every planet, every atom in your body traces its origins to that unimaginable instant, a fraction of time so dense with energy and mystery that even our most advanced science can only glimpse its edges. Today, we're going inside the universe's oldest memory, peeling back the layers of that primordial moment to uncover how the cosmos went from nothing to everything. Think about the world around you, the screen you're staring at, the air in your lungs, the ground beneath your feet. All of it was forged in the crucible of that first second. The laws of physics as we know them didn't even exist yet. Gravity, light, matter, they were all tangled together in a seething, chaotic dance at temperatures hotter than 1 trillion suns. And then, in less time than it takes for a thought to form, the universe began to take shape. But how? What forces were at play in that incomprehensible flash? Why did matter survive instead of annihilating with antimatter? Why does the cosmos look the way it does today? These aren't just abstract questions, they're the keys to understanding our very existence. This is the story of cosmic detective work, where scientists piece together clues from particle colliders, ancient light, and the fabric of space-time itself to reconstruct that first heartbeat of reality. It's a tale of quantum fluctuations smaller than atoms growing into galaxies, of hidden forces like dark matter and dark energy pulling the strings behind the scenes, and of a universe so finely tuned that the slightest change in that first second would have left us nowhere at all. By the time we're done, you won't just see the Big Bang differently, you'll see yourself differently, because every one of us is made from the remnants of that explosive beginning, stardust woven into flesh and bone. So let's step into the void, back to the moment it all began, and decode the universe's oldest memory together. The Big Bang wasn't a bang at all, at least not in the way we typically imagine explosions. Picture this: instead of a fiery blast erupting outward into empty space, think of space itself stretching, swelling, unfolding like an infinite loaf of bread rising in an oven. 13.8 billion years ago, everything we know, every galaxy, every atom, even the fabric of reality was compressed into a speck smaller than a single grain of sand. But here's the twist: that speck wasn't floating in some void. There was no outside, no before. Space and time as we know them began in that very moment. When scientists talk about the Big Bang, they're describing the sudden expansion of that primordial singularity, a point of infinite density and heat where the laws of physics as we understand them simply break down. And yet, within the tiniest fractions of that first second, the universe laid down the rules that would shape everything to come. The temperature was so extreme, over 1 trillion degrees, that matter and energy were interchangeable, flickering in and out of existence like sparks in a cosmic forge. One of the biggest misconceptions about the Big Bang is that it was some kind of chaotic explosion. In reality, it was an astonishingly orderly process. As space expanded, it cooled, allowing the fundamental forces of nature to separate like layers settling in a cosmic cocktail. First, gravity split off from the other forces. Then, the strong nuclear force which holds atoms together, and the weak nuclear force responsible for radioactive decay, went their separate ways. These divisions weren't random. They were written into the fabric of the universe, a code that would eventually allow stars to ignite and planets to form. But how do we even know any of this? The evidence isn't just theoretical. In 1965, two radio astronomers stumbled upon an eerie static signal coming from every direction in the sky, the cosmic microwave background, the afterglow of the Big Bang. This faint whisper of radiation is like a baby picture of the universe, capturing its state just 380,000 years after its birth. And if we look even closer, buried in the patterns of that ancient light, there are clues about what happened in that first unimaginable second. The story of the Big Bang isn't just about the past, it's about us. Every element in your body, from the calcium in your bones to the iron in your blood, was forged in the hearts of stars that wouldn't exist without those first critical moments. The universe didn't just create space and time, it set the stage for life itself, and that's why peeling back the layers of that first second isn't just an exercise in curiosity, it's a quest to understand our own origins. Now let's zoom in even closer, so close that time itself becomes almost meaningless. The Planck Epoch is where our understanding of the universe hits a wall, a moment so brief it makes a nanosecond feel like an eternity. From 0 to 10 to the power of -43 seconds, the cosmos was a realm of pure potential, where the familiar rules of reality hadn't yet taken shape. Imagine all the forces we know: gravity keeping your feet on the ground, electromagnetism making your phone screen glow, even the nuclear forces binding atoms, all merged into a single, unified superforce. There was no distinction between them, no separate identities. The temperature was so extreme that the very concepts of particles, energy, and even space and time, as we know them, blur into a quantum froth. This wasn't just the infancy of the universe, this was its embryonic stage, a state so alien that our current physics can't fully describe it. So how do scientists even approach studying something this incomprehensible? The key lies at the intersection of two great pillars of modern physics: quantum mechanics and Einstein's general relativity. Quantum mechanics governs the behavior of the unimaginably small, while relativity explains the fabric of space-time itself. But here's the problem: when you try to apply both at once to the Planck Epoch, they clash violently. The equations break down, spitting out nonsensical infinities. That's why this era remains one of the biggest unsolved puzzles in cosmology. Theoretical physicists have proposed wild, beautiful ideas to bridge this gap. Some suggest that at these energies, space and time cease to be smooth and continuous. Instead, they might become granular, like the pixels on a screen, but trillions of times smaller. Others speculate that extra dimensions beyond the three of space and one of time we experience could have played a role, curled up so tightly we'd never notice them today. And then there's the idea of quantum foam, a seething, turbulent sea where tiny bubbles of spacetime constantly form and vanish. What's astonishing is that even though we can't observe this epoch directly, its fingerprints might still be detectable. Some theories predict that microscopic ripples from the Planck Epoch were stretched to cosmic scales during inflation, leaving faint imprints in the large-scale structure of the universe. Others think that if we ever discover a theory of quantum gravity, a way to unify the very large and the very small, it could open a window into this primordial moment. This isn't just abstract speculation. Understanding the Planck Epoch could answer profound questions. Why does our universe have the exact blend of forces it does? Was there something before the Big Bang? And perhaps most tantalizing, did the seeds of everything we see today, from galaxies to life itself, get planted in that first flicker of existence? The Planck Epoch may be the ultimate cold case, but scientists are piecing together the clues, one revolutionary idea at a time. If the Planck Epoch was the universe's first whisper, cosmic inflation was its deafening shout. Between 10 to the power of -36 and 10 to the power of -32 seconds, something extraordinary happened. The cosmos didn't just grow. It exploded outward at a rate so staggering that the entire observable universe expanded from smaller than a proton to the size of a grapefruit in less time than it takes light to cross a single atom. This wasn't just expansion, it was exponential, doubling in size at least 100 times over. To put that into perspective, imagine blowing up a balloon to the size of the solar system, then doing it again and again before you could even blink. What caused this runaway growth spurt? The leading theory points to a mysterious field called the inflaton, a kind of cosmic energy that permeated the early universe like an invisible fuel. As this field decayed, it released energy that stretched spacetime itself, smoothing out wrinkles and irregularities like an iron pressing out the creases in fabric. This explains why the universe appears so remarkably uniform today. No matter which direction we look, the distant cosmos has nearly identical temperatures and densities, something that would be impossible without inflation ironing out the initial chaos. But here's where it gets even more fascinating. Inflation didn't just smooth things out, it also magnified tiny quantum fluctuations, the microscopic jitters left over from the Planck Epoch. These minuscule ripples, no larger than a billionth of a billionth of a billionth of a meter, were stretched to cosmic scales, becoming the seeds for everything we see today. Those faint imperfections grew into the vast web of galaxies, galaxy clusters, and cosmic voids that define the large-scale structure of the universe. Without them, the cosmos would be a featureless sea of uniformity, no stars, no planets, no us. The echoes of inflation might still be detectable in the cosmic microwave background, that ancient afterglow from the universe's infancy. Scientists scour this faint radiation for patterns called B-mode polarization, a telltale sign of primordial gravitational waves, ripples in spacetime itself, generated during inflation. Finding these patterns would be like uncovering a fossil from the universe's first moments. Experiments like the BICEP array at the South Pole and future space missions are hunting for these whispers from the dawn of time. Yet mysteries remain. Why did inflation start, and more puzzlingly, why did it stop? Some theories suggest it wasn't a one-time event but part of an eternal cycle, with new universes constantly budding off from others in an infinite multiverse. Others propose that the inflaton field didn't decay evenly, leaving behind pockets where inflation continues endlessly, creating separate bubble universes with entirely different physical laws. Cosmic inflation isn't just a theoretical curiosity, it's the bridge between the quantum weirdness of the Planck Epoch and the structured universe we inhabit today. It transformed randomness into order, chaos into cosmos, and set the stage for every galaxy, star, and planet that would follow. And as we peer deeper into the heavens, we're not just looking back in time, we're unraveling the very mechanism that made our existence possible. As the universe expanded and cooled past those first unimaginable fractions of a second, something remarkable happened. The primordial energy soup began to condense into the very first particles of matter. Between 10 to the power of -12 and 10 to the power of -6 seconds after the Big Bang, temperatures dropped to a mere trillion degrees, allowing quarks to emerge from the fading chaos. These weren't just any particles, they were the fundamental building blocks of everything tangible in the cosmos, the seeds that would eventually grow into protons, neutrons, and all the atomic nuclei that make up the world around us. Picture a cosmic cauldron more turbulent than anything we could recreate on Earth. a dense, swirling plasma where quarks and their counterparts, antiquarks, constantly formed and annihilated in flashes of energy. Gluons, the sticky particles that bind quarks together, zipped through this frenetic environment like molecular glue, struggling to hold things together against the universe's intense heat. Matter and antimatter were locked in a deadly dance, cancelling each other out in bursts of pure energy. Yet against all odds, some quarks survived. Why? The answer lies in one of nature's most subtle imbalances, a tiny preference for matter over antimatter that allowed our universe to exist at all. This quark-gluon plasma wasn't just a random mess, it followed precise rules written into the fabric of reality. The strong nuclear force, one of the universe's four fundamental interactions, began to dominate during this epoch. Imagine this force as an invisible tether between quarks, growing stronger as they tried to pull apart, like stretching an unbreakable rubber band. At these extreme energies, quarks moved nearly freely in what physicists call asymptotic freedom, a counterintuitive property where the force between them weakens at close range but becomes irresistible at a distance. This delicate balance prevented quarks from ever escaping isolation, ensuring they always combined into larger particles. The Quark Epoch set the stage for everything that followed. As the universe continued cooling, quarks finally paired up and grouped in threes, forming the first stable protons and neutrons during the subsequent Hadron Epoch. But their story didn't end there. The same quarks that flickered into existence in that searing early universe now make up your body, your phone, the stars overhead. Every atom in existence carries echoes of that primordial quark soup, a direct link back to the universe's first moments. Scientists recreate these conditions today in massive particle colliders like the Large Hadron Collider, smashing nuclei together at nearly light speed to briefly resurrect the quark-gluon plasma. These experiments reveal how quarks transition from free-flowing particles to the tightly bound structures we know today, and they're uncovering even deeper mysteries, like why there are exactly 6 types of quarks, or how their properties were fine-tuned just right to allow complex matter and life to emerge. The Quark Epoch may have lasted less than a millionth of a second, but its legacy spans the entire cosmos. Without those first quarks finding each other in the chaos, there would be no atoms, no chemistry, no planets, just an eternal sea of featureless energy. The universe's incredible journey from simplicity to complexity began here, in a fleeting moment when the first pieces of matter fought their way into existence. The universe was about to take its first real step toward becoming the structured cosmos we recognize today. Around 10 microseconds after the Big Bang, temperatures had cooled to roughly 2 trillion degrees, still unimaginably hot, but just enough for quarks to finally snap together like cosmic Lego bricks, forming the first stable protons and neutrons. This was the dawn of the Hadron Epoch, a critical transition where the building blocks of atomic nuclei locked into place. For the first time, matter wasn't just a frenzied plasma of free-floating particles, it was organizing. Quarks that had raced through the quark-gluon plasma now settled into groups of 3, bound by the strong nuclear force. Protons formed from 2 up quarks and 1 down quark, while neutrons combined 2 down quarks with 1 up. These hadrons became the universe's first semi-permanent residents, particles that would persist for billions of years rather than vanishing in flashes of annihilation. But this new stability came with a mystery that still baffles physicists. Why did matter win out over antimatter? In theory, the Big Bang should have created equal amounts of matter and antimatter, protons and antiprotons, electrons and positrons. When these opposites meet, they annihilate in bursts of pure energy. Yet today, we live in a universe dominated by matter. The tiniest imbalance, just 1 extra matter particle for every billion matter-antimatter pairs, must have survived the early chaos. This slight excess, known as baryon asymmetry, is why galaxies, stars, and planets exist at all. But what caused it? Scientists have proposed several compelling theories. One involves hypothetical particles called leptoquarks that might have treated matter and antimatter slightly differently during decays. Another points to neutrinos, ghostly particles that may have interacted asymmetrically with their antimatter counterparts. The most promising explanation involves a process called electroweak baryogenesis, where the separation of the electromagnetic and weak nuclear forces created conditions that favored matter. Experiments at particle colliders like CERN are racing to test these ideas by recreating the extreme conditions of the Hadron Epoch. This era wasn't just about survival, it set the stage for nuclear chemistry itself. The protons forged in these moments would later become hydrogen nuclei, while neutrons would enable the formation of helium and other light elements. Without this delicate transition, the periodic table would be empty and the universe would lack the raw ingredients for complexity. Yet puzzles remain. Why did quarks combine in exactly these configurations? Could different combinations have produced an alternative universe with entirely different chemistry? And if we ever discover the true source of baryon asymmetry, will it reveal deeper symmetries hidden beneath the surface of reality? The Hadron Epoch might mark the end of the universe's most violent infancy, but it left behind clues that continue to shape our quest to understand cosmic origins. Every atom in your body carries the legacy of those first protons and neutrons, a direct line stretching back to the moment matter first gained a foothold in existence. The universe had cooled just enough for a new cast of characters to take center stage. Between 1 second and about 10 seconds after the Big Bang, temperatures dipped below 1 billion degrees, still hot enough to melt atomic nuclei, but cool enough for the lightest particles to finally shine. This was the Lepton Epoch, where electrons and their elusive cousins, neutrinos, ruled the cosmos. Imagine a cosmic arena where trillions of these particles zipped through space at near light speed, colliding, annihilating, and reshaping the very fabric of reality. Electrons, the familiar particles that now power our devices and light our cities, were born in this chaotic era. But they weren't alone. For every electron, there was a positron, its antimatter twin. These pairs constantly formed from pure energy, only to collide and vanish back into gamma rays in an endless cycle of creation and destruction. The same dance played out with neutrinos, those ghostly particles that stream through your body by the billions every second without a trace. The universe was a battlefield where matter and antimatter waged total war, and the stakes couldn't have been higher. If every particle had met its antimatter counterpart, the cosmos would have dissolved into nothing but faint radiation. Yet here we are, somehow against all odds matter won. For every billion electron-positron pairs that annihilated, one electron survived. This razor-thin margin is why galaxies, planets, and people exist today. The secret might lie in the strange behavior of neutrinos. These particles are cosmic shape-shifters, oscillating between different flavors as they travel, a phenomenon that could have tipped the scales ever so slightly in matter's favor. Experiments like Japan's Super Kamiok and detector have observed this metamorphosis in action, offering clues about how these tiny particles might have saved the universe from vanishing into oblivion. The Lepton Epoch wasn't just about survival, it set the stage for the universe's next great act. As temperatures kept falling, electrons slowed down just enough to eventually be captured by atomic nuclei, forming the first complete atoms. But that wouldn't happen for another 380,000 years. For now, the cosmos was still too hot for marriage. Electrons roamed free, scattering photons in all directions and keeping the universe opaque like a dense cosmic fog. What's astonishing is how much hinged on these fleeting seconds. The balance between matter and antimatter, the behavior of neutrinos, even the eventual transparency of the universe, all were decided during this brief window. Had neutrinos behaved differently, or had the annihilation been slightly more efficient, the cosmos might have ended up a dark, empty void. Instead, the Lepton Epoch left behind just enough raw material for stars to ignite, planets to form, and life to emerge, a testament to the universe's uncanny ability to turn chaos into structure. With the universe now a few seconds old, a dramatic shift was underway. Light itself became the dominant force. This was the Photon Epoch, a sprawling era stretching from those initial chaotic moments all the way to 380,000 years after the Big Bang. Picture an ocean of pure energy where photons outnumbered matter particles by over 1 billion to 1, ricocheting endlessly through a searing hot plasma. Electrons, still too energetic to settle down, danced wildly through this glowing soup, constantly colliding with photons and scattering them like pinballs in a cosmic arcade. The entire universe was essentially a giant, opaque fog. Light couldn't travel far without being absorbed and re-emitted in a new direction. What's fascinating is how this frenetic dance preserved a secret, one we'd decode billions of years later. Every time a photon bounced off an electron, it left a tiny imprint of that interaction, a snapshot of the universe's temperature and density at that exact moment. These imprints would later become the cosmic microwave background, the oldest light we can observe today. But for now, that light was trapped, carrying information it wouldn't release for eons. Temperature was the invisible hand shaping everything during this epoch. At around 10 seconds post-Big Bang, the universe had cooled to roughly 1 billion degrees, still hot enough to keep electrons free, but now cool enough for something extraordinary to happen in the background. Protons and neutrons forged in earlier epochs began fusing into the first atomic nuclei, mostly hydrogen with a sprinkle of helium and trace amounts of lithium. This process, called Big Bang Nucleosynthesis, was like the universe's first chemistry experiment, running for about 17 minutes before temperatures dropped too low for further fusion. Yet, even as these simple nuclei formed, they couldn't yet capture electrons to become complete atoms. The ambient energy was still too intense, like a stormy sea refusing to let magnets stick together. The Photon Epoch was also a time of increasing structure. Those quantum fluctuations amplified during inflation now began to subtly influence the distribution of matter. Regions slightly denser than average started exerting a stronger gravitational pull, slowly gathering more protons and electrons toward them. This gravitational sorting happened in slow motion over hundreds of thousands of years, but it planted the seeds for all future cosmic architecture. The galaxies, galaxy clusters, and vast voids we see today all trace their origins to these faint density variations imprinted during the universe's first second and now playing out across an expanding stage. Meanwhile, the photons themselves were undergoing a remarkable transformation. As the universe expanded, stretching space-time like an infinite rubber sheet, each photon's wavelength stretched along with it. What began as high-energy gamma rays gradually redshifted into X-rays, then ultraviolet, and eventually into the microwave frequencies we detect today. This cosmic redshift is why we now see the afterglow not as a blinding flash, but as a faint microwave whisper permeating all of space. The end of the Photon Epoch, around 380,000 years after the Big Bang, marked one of the most pivotal moments in cosmic history: recombination. As temperatures fell to about 3,000 degrees, electrons finally slowed enough to be captured by nuclei, forming the first stable hydrogen and helium atoms. With electrons now bound in orbits, photons could travel freely for the first time. creating the cosmic microwave background we now observe as a snapshot of the infant universe. This moment when the fog lifted and light broke free is often called the universe's first dawn, the end of its fiery beginnings and the start of its transparent, structured future. What's astonishing is how much depended on this seemingly quiet era. The precise timing of recombination, the balance between matter and radiation, even the subtle density variations, all were fine-tuned to allow galaxies and stars to eventually form. Had photons dominated for longer, matter might never have clumped together. Had recombination happened earlier, the universe might have remained too small and dense for complexity to emerge. The Photon Epoch wasn't just a transitional phase, it was the universe's incubation period where the invisible groundwork was laid for everything to come. The universe was about to perform its first act of alchemy, transforming the simplest building blocks into the first atomic nuclei. Between 1 second and 3 minutes after the Big Bang, temperatures dropped from 10 billion to just under a billion degrees, creating the perfect conditions for protons and neutrons to fuse in a process called Big Bang Nucleosynthesis. This wasn't just a minor event, it was the moment the periodic table got its first 2 entries, hydrogen and helium, the cosmic ingredients that would later fuel stars and shape galaxies. Picture the scene, a searing plasma where free protons, hydrogen nuclei, and neutrons zipped through space at unimaginable speeds. As the universe expanded and cooled, these particles began sticking together in pairs and triplets. First, a proton and neutron combined to form deuterium, a heavy isotope of hydrogen. Then, like a cosmic assembly line, these deuterium nuclei collided with more protons and neutrons, forming helium-3 and eventually stable helium-4. The numbers were precise. For every 12 hydrogen nuclei, about 1 helium nucleus formed a ratio we still see in stars and gas clouds today. But here's the puzzle. Why didn't this process continue to forge heavier elements like carbon or iron? The answer lies in the universe's breakneck expansion. After just 17 minutes, temperatures plummeted below 100 million degrees, too cold for nuclear fusion to continue. The density of particles had also thinned out dramatically, making collisions increasingly rare. Without the extreme heat and pressure found later in stellar cores, the cosmos simply couldn't cook elements beyond lithium, the third lightest element. This delicate timing reveals how finely tuned the early universe was. Had expansion been slightly slower, more helium might have formed, altering the future of star formation. Faster expansion could have left the universe with almost no helium at all. Even tiny changes in the strength of the nuclear force would have dramatically shifted these ratios, potentially rendering the cosmos incapable of building complex chemistry. Scientists test these predictions by studying primordial gas clouds, relics from the early universe that have avoided stellar contamination. Their chemical fingerprints match Big Bang nucleosynthesis calculations with astonishing precision, confirming our understanding of those first 3 minutes. Yet mysteries remain, like the lithium problem. Why observed lithium levels are 3 times lower than predicted? Some theories suggest unknown particle interactions or early stellar processes might have scrubbed lithium from the cosmic record. What's awe-inspiring is how these first nuclei became the raw material for everything to come. Every star in the night sky, every planet orbiting them, and every molecule in your body owes its existence to that brief window when the universe was cool enough to fuse nuclei, but still hot enough to forge them in abundance. The simplicity of Big Bang nucleosynthesis wasn't a limitation. It was the foundation for all the complexity that followed. 380,000 years after the Big Bang, the universe finally took its first baby picture, a cosmic selfie etched in microwaves that we're still deciphering today. This is the cosmic microwave background, or CMB, the oldest light in existence. Imagine a fog lifting after an endless night, revealing a universe no longer opaque with plasma but suddenly transparent. A moment when photons broke free from their endless collisions with electrons and began streaming unimpeded across space. That flash of liberation created an afterglow so enduring that 13.8 billion years later, we can still detect its faint whisper in every direction of the sky. What makes the CMB so extraordinary isn't just its age, it's the wealth of information encoded in its subtle variations. When the first atoms formed during recombination, photons finally traveled freely, carrying with them a precise snapshot of the universe at that exact moment. Today, that light arrives cooled to just 2.7 degrees above absolute zero, stretched by cosmic expansion into microwaves. But hidden within those microwaves are temperature fluctuations, tiny hotspots, and cold spots differing by mere millionths of a degree. These imperfections are like cosmic hieroglyphs, telling the story of the universe's earliest structure. Scientists decode this story using satellites like Planck and WMAP, which map the CMB with breathtaking precision. The patterns they reveal are nothing short of a blueprint for reality. Those slightly denser regions, they're the gravitational seeds that would later grow into galaxies and galaxy clusters. The exact spectrum of the CMB's light, it confirms the universe's composition: 5% ordinary matter, 27% dark matter, and 68% dark energy, numbers that align perfectly with other cosmic measurements. Even the polarization of this ancient light carries clues, potentially revealing evidence of primordial gravitational waves from inflation. But the CMB isn't just a relic, it's a time machine. By analyzing its subtle distortions, astronomers can peer even further back than 380,000 years. The way light slightly bends around massive galaxy clusters, a phenomenon called gravitational lensing, allows us to map the distribution of dark matter. And the large-scale patterns in the CMB align eerily with the positions of modern superclusters, showing how the universe's infancy directly shaped its adulthood. Perhaps most astonishing is how perfectly this afterglow matches theoretical predictions. The CMB's near uniformity supports the inflationary model, while its tiny fluctuations explain why the cosmos isn't a featureless void. It's as if the universe left us a carefully crafted message in a bottle, drifting across billions of years just to confirm we're on the right track in decoding its origins. Yet mysteries remain. Why does one hemisphere of the CMB show slightly larger fluctuations than the other? Could this axis of evil, as scientists whimsically call it, hint at pre-Big Bang physics? And what might future telescopes with even greater sensitivity uncover in this primordial light? The CMB isn't just a static image, it's a dynamic puzzle that continues to challenge and inspire, reminding us that every time we look up, we're gazing into the universe's deepest memory. Deep within the quantum foam of the early universe, something extraordinary was stirring, fluctuations so small they defied measurement, yet destined to shape the entire cosmos. In the first trillionth of a second, space-time itself bubbled with microscopic ripples, temporary distortions where particles and energy flickered in and out of existence like static on a cosmic radio. These weren't random defects, they were the universe's first brushstrokes, quantum imperfections that inflation would later stretch across the sky, imprinting the blueprint for everything from galaxy clusters to the voids between them. The mechanism behind these fluctuations lies in Heisenberg's uncertainty principle, which states that on the smallest scales, empty space can never be perfectly still. Virtual particle pairs constantly emerge and vanish, borrowing energy from the vacuum before returning it in an endless quantum dance. During inflation, These fleeting ripples were frozen into the fabric of space-time as the universe expanded faster than light itself could cross a single atom. What began as quantum jitter smaller than a proton became magnified to cosmic proportions, like stretching a fingerprint to the size of a continent. We see the legacy of these fluctuations every time we map the cosmic microwave background. Those subtle temperature variations, hot spots and cold spots differing by mere millionths of a degree, mirror the original quantum seeds. Denser regions pulled in more matter through gravity, growing over billions of years into the galaxies we observe today. Meanwhile, less dense areas evolved into vast cosmic voids. The entire large-scale structure of the universe, from the filaments of the cosmic web to the positions of individual galaxy clusters, can be traced back to those initial quantum hiccups. But the real mystery isn't just how these fluctuations grew, it's why they had exactly the right amplitude to create a universe hospitable to life. Too strong, and matter would have clumped into black holes before stars could form. Too weak, and gravity couldn't overcome the expansion, leaving the cosmos a featureless haze. Some theories suggest deeper physics at play, perhaps extra dimensions vibrating in higher dimensional space, or fields beyond the inflattened subtly tuning the quantum noise. Others propose these fluctuations are echoes from a pre-Big Bang universe, imprinted like fingerprints on the surface of a bubble in a quantum multiverse. Experiments like the Bicep Array hunt for primordial gravitational waves, ripples in spacetime that could confirm quantum fluctuations were stretched by inflation. Meanwhile, galaxy surveys like Euclid map how these early seeds evolved into today's cosmic web. Together, they form a detective story spanning 13.8 billion years, where the smallest quantum events birthed the grandest structures in existence. What's humbling is realizing that every star, every planet, even the atoms in your hands exist because of these microscopic tremors in the first second. The universe didn't grow smooth or random, it grew precise, with quantum uncertainty woven into its very foundations. And as we decode these patterns, we're not just studying the past, we're reading the hidden language of cosmic creation itself. The universe had an invisible architect, one that shaped everything we see today without ever revealing itself. Dark matter, this mysterious substance that neither emits nor absorbs light, was already weaving its gravitational web in the first seconds after the Big Bang. While ordinary particles like quarks and electrons jostled in the searing plasma, dark matter drifted through the chaos untouched, its gravity gently tugging at the fabric of the young cosmos. Without this unseen hand, galaxies might never have formed, and the universe would be a vast, empty expanse. Here's the astonishing part: dark matter didn't just influence structure formation, it dictated the entire timeline. Ordinary matter, bathed in the intense radiation of the early universe, was constantly buffeted by photons, making it difficult for clumps to grow. But dark matter, indifferent to light's push and pull, began collapsing into dense patches almost immediately. These invisible scaffolds became gravitational wells, pulling in ordinary matter like cosmic magnets once the universe cooled enough. The result: a delicate dance where dark matter laid the foundation and visible matter followed, eventually igniting the first stars. The hunt to identify dark matter's true nature is one of science's greatest detective stories. Leading candidates include WIMP, weakly interacting massive particles, hypothetical entities that barely interact with normal matter except through gravity. Others propose actions, ultra-light particles born from quantum field fluctuations in the early universe. Then there's the possibility that dark matter isn't a particle at all but a manifestation of modified gravity, though evidence like the bullet cluster, where dark matter and visible matter separate during galaxy collisions, strongly suggests it's something tangible. What's particularly intriguing is how dark matter's origins might trace back to the universe's very first instance. Some theories suggest it was forged during the Quark Epoch, a byproduct of symmetry breaking events that also gave rise to ordinary matter. Others speculate it's a relic from before the Big Bang, a shadowy remnant of a previous cosmic cycle. Experiments like the Large Hadron Collider and deep underground detectors such as LUX Zeppelin are racing to catch a fleeting interaction that could finally unveil dark matter's identity. The implications go far beyond astrophysics. If dark matter particles are discovered, they could open doors to entirely new branches of physics, rewriting our understanding of mass, energy, and the fundamental forces. And if they're fundamentally different from anything predicted, well, that might be even more exciting. The early universe's hidden scaffolding remains one of cosmology's most tantalizing puzzles, a reminder that what we can't see often holds the keys to everything we can. Just when cosmologists thought they had the universe figured out, it threw them a curveball, one that would rewrite the textbooks. In 1998, two teams studying distant supernova made a shocking discovery. The universe wasn't just expanding, it was accelerating, as if some invisible force was pushing galaxies apart faster and faster over time. This cosmic repellent became known as dark energy, and it makes up a staggering 68% of the universe's total energy budget. But here's the real twist: this mysterious force might have been there from the very beginning, subtly shaping the cosmos in its first second of existence. The leading theory suggests dark energy is the cosmological constant, a term Einstein originally added to his equations to keep the universe static, later calling it his greatest blunder when the expansion was discovered. But in light of acceleration, this constant might not have been a mistake after all. Imagine it as an energy woven into the fabric of spacetime itself, a kind of anti-gravity that grows stronger as the universe expands. In the first moments after the Big Bang, when space was unimaginably dense, dark energy's push would have been negligible compared to the violence of inflation and particle collisions. But as matter thinned out over billions of years, its influence became dominant, like a whisper turning into a shout across cosmic time. Could dark energy have played a role in the first second? Some models suggest it might have influenced inflation's abrupt end, acting as a cosmic brake that halted the universe's exponential growth. Others propose even wilder ideas, that dark energy isn't constant but evolves over time, or that it's tied to undiscovered particles that emerged alongside quarks and gluons. Then there's the phantom energy hypothesis, a scenario where dark energy's strength increases indefinitely, eventually ripping apart galaxies, stars, and even space-time in a catastrophic Big Rip trillions of years from now. The stakes couldn't be higher. Dark energy doesn't just explain the universe's current expansion, it holds the key to its ultimate fate. Will acceleration continue steadily, leaving galaxies isolated in a cold, dark future? Could dark energy eventually reverse, collapsing the cosmos back into a singularity? Or is our understanding fundamentally flawed, requiring new physics beyond Einstein's relativity? Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope aim to map billions of galaxies, searching for clues in the large-scale structure of the universe. What makes dark energy so perplexing is how little we know compared to how much it controls. It's the ultimate cosmic puppeteer, invisible yet omnipresent, silent yet shaping everything. And if we ever unravel its origins, whether in the first second or some deeper quantum reality, we won't just solve a mystery, we'll discover the final chapter of the universe's story before it's even written. What if our universe isn't the only one? Imagine a cosmic foam where each bubble is an entirely separate universe with its own unique physics. some where gravity is stronger, others where atoms never formed, or even stranger realities where time flows backward. This is the multiverse theory, a radical idea suggesting that the conditions of our universe, the precise strength of gravity, the exact mass of electrons, even the existence of life itself, might just be a cosmic roll of the dice. And here's the mind-bending part. The outcome of that roll could have been decided in the very first second after the Big Bang. The concept hinges on a process called eternal inflation, where the rapid expansion of space-time didn't just happen once but continues endlessly in a sea of higher dimensional space. Picture a pot of water boiling over, with new bubbles constantly forming, each a self-contained universe with its own Big Bang. In this scenario, our universe is just one bubble among countless others, each with different fundamental constants. Some might collapse instantly, while others could harbor exotic forms of matter or life we can't even fathom. The key question is, did the quantum fluctuations of the first second lock our bubble into its particular set of physical laws, or was it purely random chance? One compelling clue comes from the fine-tuning problem. Our universe's constants appear eerily balanced for life. Adjust the strength of the strong nuclear force by even a few percent, and stars might never ignite. The multiverse offers an elegant, if unsettling, explanation. With infinite variations, some universes inevitably hit the jackpot. But this isn't just speculative cosmology, it's testable science. If adjacent bubbles ever collided with ours, they might leave imprints in the cosmic microwave background, like bruises on space-time. Telescopes are actively searching for these signatures, though none have been found yet. Philosophers grapple with the implications too. If every possible universe exists, does that diminish the meaning of our own? Or does it amplify the wonder that we find ourselves in one where galaxies, planets, and consciousness could emerge? The multiverse blurs the line between physics and metaphysics, challenging us to rethink not just how the universe began, but what existence even means. For now, the multiverse remains a hypothesis, one that stretches our imagination to its limits. But whether it's confirmed or debunked, the pursuit reveals something profound. The first second of our universe might not have been a solitary event, but one note in an infinite cosmic symphony. String theory rewrites the rules of reality itself, not with particles, but with tiny, vibrating strands of energy no larger than the Planck length. These aren't just theoretical curiosities. They could be the missing key to understanding the universe's first chaotic second. While traditional physics stumbles at the Big Bang's infinite densities, string theory offers a way forward, suggesting that what we call a singularity might instead have been a dense, vibrating tapestry of strings, each oscillation defining a different particle or force. Picture the early universe as a cosmic symphony, where every quark, photon, and gluon is a note played by these microscopic strings. The pitch of their vibration determines whether they become matter or carry forces, blending quantum mechanics and gravity into a single framework. This harmony could resolve the century-old clash between Einstein's relativity, which governs the vast cosmos, and quantum mechanics, which rules the subatomic world. In the first second, when both realms were indistinguishable, string theory proposes they were united by these vibrating threads, but the implications go deeper. String theory requires extra dimensions, tiny, curled-up spaces beyond the three we experience. Some models suggest these dimensions unfurled during inflation, shaping the universe's fundamental forces. Others propose that collisions between higher dimensional membranes of spacetime triggered the Big Bang itself. If true, our universe might be one page in a multidimensional book, with the first second marking the moment our chapter began. Critics argue string theory lacks experimental proof, but its mathematical elegance is undeniable. It naturally predicts gravity's existence, something quantum field theories struggle with, and offers plausible explanations for cosmic fine-tuning, like why the universe's constants are so perfectly balanced for life. Future experiments, like observing primordial gravitational waves or detecting extra dimensions in particle colliders, could turn speculation into revelation. What's breathtaking is the possibility that the universe's oldest memory isn't written in particles or forces, but in the resonant hum of strings, a vibration that still echoes through every atom today. A trillionth of a second after the universe burst into existence, something extraordinary happened. An invisible field snapped on like a cosmic light switch, transforming the chaotic soup of massless particles into the building blocks of reality as we know it. This was the Higgs field, the universe's ultimate game-changer, a silent energy permeating all of space that would endow particles with the gift of mass. Picture a grand cosmic party where photons zip through the crowd effortlessly, while electrons, quarks, and other particles wade through like they're stuck in molasses. That sticky resistance is the Higgs field at work, interacting with particles to give them their heft. The discovery of the Higgs mechanism in 2012 at CERN Large Hadron Collider was a triumph decades in the making. Scientists had theorized since the 1960s that this field must exist to explain why some particles have mass while others, like light itself, don't. The Higgs boson, the field's telltale particle, was the final piece of the Standard Model puzzle, a fleeting ripple in the field that confirmed our understanding of how mass arises. But how did this field emerge in the early universe? As temperatures cooled below a quadrillion degrees, the Higgs field underwent what physicists call symmetry breaking, a phase transition similar to water freezing into ice. Before this moment, particles raced around at light speed, weightless and free. Afterward, the field condensed, and suddenly, certain particles began dragging as if moving through an invisible cosmic trickle. What's fascinating is how selectively the Higgs field interacts with particles. Protons and neutrons, which make up atoms, get nearly all their mass not from the Higgs directly, but from the binding energy of the strong nuclear force holding their quarks together. Electrons, on the other hand, owe their entire mass to the Higgs, and without just the right electron mass, atoms couldn't form stable structures, chemistry would be impossible, and life as we know it couldn't exist. This delicate balance raises profound questions. Why does the Higgs field have precisely the strength it does? If it were slightly stronger, particles would be too heavy to form complex matter. Slightly weaker, and the universe might lack gravity's grip to pull matter together into stars and planets. The Higgs field isn't just a relic of the early universe. It's actively shaping reality right now. Every time you push against a wall or feel the weight of your body, you're experiencing the lingering effects of that trillionth of a second transition. Some theories suggest the field's current state might not be permanent. In a hypothetical false vacuum scenario, a quantum fluctuation could someday drop it to a lower energy level, rewriting the laws of physics in an instant. While unlikely, this underscores how deeply our universe's structure depends on this fragile, invisible scaffold. Unraveling the Higgs field's origins goes beyond particle physics. It touches on cosmology's greatest mysteries. Did inflation set the stage for the Higgs phase transition? Could variations in the field explain why our universe has matter but other hypothetical ones don't? As colliders probe ever higher energies and telescopes peer deeper into cosmic history, we're not just studying how particles get mass, we're uncovering the hidden architecture that made atoms, chemistry, and life itself possible. Of all the particles that flooded the young universe, none are more elusive or more consequential than neutrinos. These ghostly particles, so light they were once thought to be entirely massless, pass through entire planets like they're not even there. 1 trillion neutrinos stream through your body every second, leaving no trace, as if reality itself were a hologram to them. Yet in the first second after the Big Bang, these phantoms weren't just bystanders. They were key players in one of the cosmos' greatest mysteries, why anything exists at all. When the universe was just 1 second old, neutrinos outnumbered protons and electrons by a factor of 1 billion. They darted through the searing plasma like cosmic bullets, barely interacting with other particles, yet influencing everything through their sheer abundance. This was the Lepton Epoch, where neutrinos and their charged cousins electrons and positrons dominated the energy budget of the cosmos. But unlike electrons, which would later combine with nuclei to form atoms, neutrinos refused to settle down. Their aloof nature meant they decoupled from matter earlier than any other particle, escaping the primordial soup while photons were still trapped in a fog of collisions. What makes neutrinos so fascinating is how they might have tipped the scales in matter's favor. According to the laws of physics, the Big Bang should have created equal amounts of matter and antimatter. Protons and antiprotons, electrons and positrons, neutrinos and antineutrinos. When these pairs meet, they annihilate in bursts of pure energy. Yet today, we live in a universe made almost entirely of matter. The only way this could happen is if some tiny asymmetry, 1 extra matter particle per billion annihilations, survived the early chaos. Neutrinos, with their subtle preference for matter over antimatter, could hold the answer. Recent discoveries have shown that neutrinos oscillate, changing between 3 different flavors: electron, muon, and tau as they travel. This shape-shifting behavior suggests they have mass, albeit vanishingly small. More intriguingly, if antineutrinos oscillate at slightly different rates, it could explain why matter gained the upper hand. Experiments like Japan's T2K and the upcoming Deep Underground Neutrino experiment are hunting for this discrepancy, which might finally solve the riddle of our universe's existence. But neutrinos' role didn't end there. Their early departure left fingerprints on the cosmic microwave background, subtly altering how matter clumped together in the universe's first moments. Even now, relic neutrinos from the Big Bang, known as the cosmic neutrino background, permeate space at nearly light speed. Unlike the photon afterglow we detect as microwaves, these neutrinos are too low energy to observe directly. Yet their gravitational influence shaped the distribution of galaxies we see today. The most mind-bending possibility: some theories suggest neutrinos could be their own antiparticles, a property that would make them unique among fundamental particles. If true, rare nuclear decays might produce them without antineutrino counterparts, offering another path to the matter-antimatter imbalance. Experiments like Germany's CATRIN aim to weigh neutrinos with unprecedented precision, while others search for these exotic decays in underground labs shielded from cosmic rays. Neutrinos remind us that the universe's most important actors aren't always the most visible. Their ghostly whispers, echoing from the first second of time, carry secrets we're only beginning to decode, secrets that might explain why stars shine, planets form, and life itself emerged from the chaos. Among the most tantalizing possibilities from the universe's first heartbeat is the idea that black holes, those cosmic vacuum cleaners we associate with dying stars, might have formed in the very first second of existence. Not the colossal giants we observe today, but microscopic ones, smaller than an atom yet heavier than a mountain, born from the violent density fluctuations of the newborn cosmos. These hypothetical objects, called primordial black holes, could be lurking all around us, invisible relics of the Big Bang's chaos, and they might hold answers to some of astronomy's biggest mysteries. Picture the universe in its first fraction of a second, a seething maelstrom where quantum jitters in spacetime itself created pockets of extreme density. In regions where matter and energy piled up just a little too densely, gravity could have overcome all other forces, collapsing these spots into tiny black holes. Unlike stellar black holes, which form from collapsing stars and weigh at least several times our sun's mass, primordial black holes could range from the mass of a small asteroid to thousands of times the sun, all compressed into a space smaller than a proton. Their size wouldn't make them any less bizarre. According to Hawking radiation, these tiny black holes should glow like embers, losing mass over time until they potentially vanish in a flash of gamma rays. What makes this idea so compelling is how it could solve two puzzles at once. First, dark matter, that invisible glue holding galaxies together, might actually be a sea of primordial black holes drifting unseen through space. While most searches for dark matter focus on exotic particles, these ancient black holes could have been hiding in plain sight, their gravity shaping the cosmos without emitting a single photon. Second, some theories suggest these black holes might be more than just cosmic debris. They could be portals. Inside each one's event horizon, space and time might twist into a new universe with its own Big Bang and physical laws. Our entire universe could theoretically reside inside a primordial black hole from a parent cosmos, like a Russian nesting doll of realities. The hunt for these objects is already underway. Scientists scan old photographic plates for flashes of light that might betray a tiny black hole passing in front of a star, bending its light like a lens. Others listen for the distinctive chirp of merging primordial black holes in gravitational wave detectors. Even the unexpected ripples in the early universe's light, the cosmic microwave background, could carry imprints of their presence. So far, no definitive evidence has been found, but the search has only narrowed the possible mass ranges where they might exist. Yet the implications stretch beyond astrophysics. If primordial black holes exist, they could rewrite our understanding of the universe's infancy. Their formation would require conditions far more extreme than we've assumed, hinting at exotic physics in that first second, perhaps even a phase transition in the fabric of space-time itself. And if they're out there silently shaping the cosmos, we're left with a humbling thought. The universe's oldest shadows might still be with us, hiding in the dark between the stars. At the moment of the Big Bang, our cosmic clock seems to reset, but does that mean time itself began? This is the information paradox, one of physics' most profound puzzles. Our equations dissolve into infinities when we try to peer beyond that primordial instant, as if reality hit a cosmic Control plus Alt plus Delete. Yet the human mind rebels at the idea of absolute nothingness before time. Was there truly no before, or are we missing a deeper layer of cosmic memory? One compelling theory suggests our universe isn't a one-time event but part of an endless cycle of expansion and contraction, a cosmic heartbeat. In this Big Bounce scenario, a previous universe collapsed into an ultra-dense state before rebounding as our Big Bang. The laws of quantum mechanics might allow spacetime to survive such extremes, preserving information across cycles like a cosmic hard drive. Imagine galaxies from a prior universe compressed into quantum fluctuations that later seeded our own cosmic structures, an elegant symmetry where endings birth new beginnings. Then there's the multiverse angle. If our universe is one bubble in a frothing sea of higher dimensional space, before might simply mean elsewhere. Other bubble universes could have entirely different timelines, their Big Bangs unrelated to ours. Some theories even propose that black holes in other universes spawn new ones, creating an infinite fractal of cosmic births. The information we think was lost might simply have crossed into dimensions beyond our perception. String theory offers another twist, a landscape of possible universes where the Big Bang was a transition between states. Picture a higher dimensional brain, short for membrane, colliding with another, releasing energy that crystallized into our four-dimensional spacetime. In this view, asking what happened before our Big Bang is like a fish asking what existed before the ocean. It's the wrong framework entirely. Yet all these ideas share a common challenge: the limits of observation. Without light or particles from a pre-Big Bang era, how can we test these theories? Some scientists search for faint imprints in the cosmic microwave background, circular patterns that might betray a previous universe's collisions. Others study quantum entanglement, where particles remain mysteriously linked across space, as a clue to deeper cosmic connections. Perhaps the boldest idea comes from loop quantum gravity, which suggests time itself might be granular. At the Planck scale, the distinction between before and after could blur like a pixelated image, making the question meaningless. In this view, the Big Bang wasn't a beginning but a transformation, like ice melting into water, where before simply refers to a different phase of quantum spacetime. What's striking is how these theories transform the paradox from a wall into a doorway. Whether through cycles, brains, or quantum foam, they suggest our universe's birth might be part of something vaster, a single note in an eternal symphony of cosmic reinvention. The mystery of before isn't just about origins. It's about whether existence itself follows rules we're only beginning to glimpse. Imagine a universe where all forces were identical, where gravity, electromagnetism, and the nuclear forces behaved exactly the same way. No stars would shine, no atoms would bond, and life as we know it would be impossible. Yet in the first searing moments after the Big Bang, this was almost the case, a perfect symmetry where all fundamental forces were unified into a single, seamless interaction. Then, as the cosmos expanded and cooled, something remarkable happened. Those symmetries shattered like a pane of cosmic glass, creating the diverse forces that shape our reality today. This process, called symmetry breaking, is one of the most pivotal and mysterious events in cosmic history. In the universe's infancy, temperatures were so extreme that particles and forces existed in a state of perfect symmetry. The electromagnetic and weak nuclear forces, which now govern everything from chemistry to radioactivity, were indistinguishable, a single electroweak force. Even the strong nuclear force, which binds atomic nuclei, might have been unified with the others at even higher energies, but as the universe expanded, it crossed critical temperature thresholds, triggering phase transitions akin to water freezing into ice. With each transition, a symmetry broke and new forces emerged with distinct properties. The first to separate was gravity, peeling away from the other forces during the Planck Epoch. Next, the strong nuclear force split off, followed by the separation of the electromagnetic and weak forces. These divisions weren't random. They were dictated by the underlying quantum fields that permeate reality. But here's the puzzle. Why did these symmetries break in precisely the way they did? The Higgs field, which gave particles mass, could have condensed differently, altering the strengths of the forces or even preventing some particles from gaining mass at all. The strong nuclear force, for instance, is perfectly tuned, just strong enough to bind protons and neutrons, but weak enough to allow stars to fuse hydrogen. If it were slightly stronger, all hydrogen would have fused into helium immediately after the Big Bang, leaving no fuel for stars. Slightly weaker, and no stable nuclei would form at all. One compelling theory suggests these breaks weren't accidents but inevitable outcomes of deeper physics. The vacuum landscape hypothesis proposes that the universe's quantum fields could settle into different low-energy states, much like a ball rolling into one of many valleys in a hilly terrain. Our universe landed in a valley where the forces and particle masses allow for complexity and life. Other valleys might correspond to entirely different physics, with some universes having no electromagnetism or gravity too weak to form galaxies. The echoes of symmetry breaking are everywhere. The imbalance between matter and antimatter might trace back to asymmetries in how particles interacted during these phase transitions. Even the cosmic microwave background carries faint imprints of these breaks, like fossils in the light of the infant universe. Experiments like the Large Hadron Collider recreate these extreme conditions, slamming particles together to glimpse how symmetries might have fractured in the first moments. Yet mysteries linger. Did symmetries break uniformly across the cosmos, or could distant regions have different physics? Could multiple symmetry-breaking events explain dark matter or dark energy? And most tantalizingly, was our universe's particular set of breaks inevitable, or a stroke of cosmic luck? The answers might lie in the elusive theory of everything, a framework that could unite quantum mechanics and gravity, and reveal why our universe's shattered symmetries led to a world rich enough for atoms, planets, and curious minds to ponder their own origins. Consider this staggering fact: if the strength of gravity were just slightly weaker, stars wouldn't form. If the nuclear forces were marginally stronger, hydrogen would have fused into heavier elements instantly after the Big Bang, leaving no fuel for suns. Even the tiniest tweak to the universe's constants would render life impossible. This eerie precision isn't coincidence. It's the Anthropic Principle in action, the observation that our universe's laws appear meticulously calibrated to allow conscious observers like us to exist. But how is this fine-tuning a cosmic fluke, or does it hint at something deeper beneath the fabric of reality? One camp argues we're witnessing survivorship bias on a universal scale. In an infinite multiverse where countless universes bubble into existence with random physical constants, some will inevitably hit the jackpot. We find ourselves in one of the lucky few where conditions permit galaxies, planets, and biochemistry, not because the universe was designed for life, but because life can only arise in a universe that permits it. It's like a puddle marveling at how perfectly its hole fits its shape, unaware of the countless other puddles that evaporated or spilled. The multiverse theory transforms fine-tuning from a mystery into a statistical inevitability. Yet others see a more profound puzzle. Even within our universe, the chain of prerequisites for life is absurdly narrow. Carbon, the backbone of organic chemistry, exists only because of a precise resonance in the helium fusion process. Water's unique properties, its expansion when frozen, its surface tension depend on exact quantum mechanical balances. The cosmological constant, which governs the universe's expansion rate, is fine-tuned to 1 part in 10 to the power of 120. Random chance starts to feel inadequate as an explanation. Could there be undiscovered physics, a deeper law or principle, that necessitated these values? Some theorists propose a theory of everything might reveal these constants aren't arbitrary but mathematically inevitable, like pi or the Fibonacci sequence. The Anthropic Principle also blurs the line between science and philosophy. If the universe's laws seem improbably hospitable, does that imply a designer? Not necessarily, but it does force us to confront the limits of reductionist thinking. Perhaps consciousness plays a more fundamental role in reality than we've assumed. Quantum mechanics already shows that observation affects the observed. Could the universe's laws be entangled with the presence of observers in ways we don't yet grasp? Experiments may one day test these ideas. If the multiverse exists, collisions between bubble universes could leave scars in the cosmic microwave background. Alternatively, a unified theory might derive constants like the electron's mass from first principles, removing the illusion of fine-tuning altogether. Until then, the Anthropic Principle remains a mirror reflecting back our deepest questions about existence. Whether through infinite universes or undiscovered physics, the answer will reshape not just cosmology, but our very understanding of what it means to be here now, in this peculiarly life-friendly cosmos. Peering into the universe's first second requires more than just theory. It demands experiments that push the boundaries of human ingenuity. On Earth, colossal machines like the Large Hadron Collider act as time machines, recreating conditions not seen since the Big Bang's fiery dawn. By smashing protons together at 99.999999% the speed of light, the LHC briefly resurrects temperatures 100,000 times hotter than the sun's core, letting physicists witness how quarks and gluons behaved when the universe was just a trillionth of a second old. These collisions aren't just recreations, they're revelations, producing exotic particles like the Higgs boson that validate long-held predictions about how mass emerged in the infant cosmos. But Earth-bound experiments only tell part of the story. To truly understand the universe's birth, we must also look outward, far outward. Telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Observatory function as cosmic historians, capturing light that's traveled for billions of years. When Webb observes galaxies formed just 300 million years after the Big Bang, it's not just seeing ancient stars, it's detecting the aftermath of those first critical seconds, when quantum fluctuations stretched by inflation began collapsing into gravitational wells. Even more remarkably, observatories like the South Pole Telescope study the cosmic microwave background with such precision that they can map the density variations of the early universe down to 1 part in 100,000 fossilized ripples from the universe's quantum infancy. The synergy between these approaches is what makes modern cosmology so powerful. Particle colliders reveal the microphysics of the early universe, while telescopes trace how those microscopic processes scaled up to shape the cosmos. Together, they've uncovered startling connections like how the quark-gluon plasma created in heavy ion collisions behaves like a near-perfect fluid, mirroring the properties predicted for the universe's first microseconds. Or how measurements of the cosmic microwave background align with collider data to pin down the universe's composition with unprecedented accuracy. Yet the most exciting discoveries often lie in the discrepancies. When the LHC found the Higgs boson was slightly lighter than some theories predicted, it forced physicists to reconsider how the Higgs field might have interacted with dark matter in the early universe. Similarly, when telescopes like Planck detected unexpected large-scale anomalies in the cosmic microwave background, subtle asymmetries nicknamed the axis of evil, it sparked debates about whether inflation truly happened as we think, or if something even stranger occurred in those first moments. Future experiments promise to peel back even more layers of the cosmic onion. The proposed future circular collider could reach energies 7 times higher than the LHC, potentially uncovering particles that mediated the unification of forces in the universe's first nanosecond. Meanwhile, next-generation gravitational wave detectors like LISA might catch echoes from cosmic phase transitions, the space-time ripples produced when the Higgs field switched on or dark matter decoupled from normal matter. And projects like CMB-S4 aim to measure the polarization of the cosmic microwave background with such sensitivity that they could detect the imprint of primordial gravitational waves, offering direct evidence for inflation. What's astonishing is how much we've learned and how much remains hidden. Every new experimental frontier reveals both answers and deeper questions, like an endless cosmic matryoshka doll. The first second of the universe may be locked in the distant past, but through the combined power of colliders and telescopes, we're slowly deciphering its secrets, one subatomic collision and one photon from the edge of time at a time. For all our telescopes, colliders, and equations, the universe's first second guards its secrets fiercely. We've reconstructed cosmic history back to trillionths of a second after the Big Bang with astonishing precision. Yet the closer we get to time zero, the more the laws of physics dissolve into paradox. General relativity predicts a singularity of infinite density, while quantum mechanics demands discrete particles can't occupy the same space. Both can't be true, which means our current understanding is fundamentally incomplete. This isn't just a gap in knowledge, it's a chasm where the very framework for asking questions breaks down. Consider the Planck Epoch, that unfathomably brief span from 0 to 10 to the power of -43 seconds. At these scales, spacetime itself may have been a seething quantum foam, bubbling with virtual black holes and extra dimensions. But here's the catch: to probe this era, we'd need a particle accelerator the size of the Milky Way. Even if we built one, the energy required would recreate the conditions we're trying to study, essentially making a new universe in the lab. The irony is poetic. To observe creation, we might have to become creators ourselves, an ethical and practical frontier we're nowhere near crossing. Then there's the problem of cosmic forgetfulness. Inflation erased nearly all traces of what came before it, stretching quantum fluctuations into galactic seeds while overwriting any earlier imprints. It's like trying to reconstruct a burned book from the ashes, except the ashes are still scattering at light speed. Some theorists suggest primordial gravitational waves or subtle anomalies in the cosmic microwave background could carry whispers from beyond the inflationary veil. Others argue the universe might be fundamentally unknowable past a certain point, with physical laws emerging anew at the Big Bang like a computer rebooting. Yet history teaches us that every unknowable has eventually fallen to human curiosity. Black holes were once dismissed as mathematical oddities. Now we photograph their shadows. The Higgs boson took 50 years to detect, but detect it we did. Future breakthroughs, quantum gravity theories, space-based interferometers, even AI-driven simulations could crack open the Planck Epoch's mysteries. Or they might reveal deeper layers of questions, like peeling an infinite cosmic onion. Perhaps the most humbling thought isn't that we'll never know, but that the universe's first secrets might require entirely new ways of thinking. Just as relativity shattered Newton's clockwork cosmos, the next revolution could redefine time, causality, or even what we consider real. The journey to decode the first second isn't just about filling gaps, it's about discovering what questions we're not yet wise enough to ask. The moment the universe burst into existence isn't merely a scientific frontier, it's a mirror reflecting humanity's deepest questions about meaning, purpose, and origin. Across cultures and centuries, theologians and philosophers have grappled with the mystery of creation, weaving narratives that both contrast and complement the scientific story. Where cosmology sees quantum fluctuations and inflationary expansion, spiritual traditions perceive the hand of the divine or the unfolding of a cosmic plan. This interplay isn't a clash but a conversation, one that expands our understanding of what it means to exist at all. Take the ancient concept of creatio ex nihilo, a creation from nothing. In Christian theology, this idea frames the universe as a deliberate act of God, conjured into being without pre-existing material. Augustine of Hippo, writing in the 4th century, wrestled with the nature of time itself, suggesting it was born alongside the cosmos rather than preceding it. This resonates strikingly with modern cosmology's assertion that time began with the Big Bang. Yet where science stops at the how, theology ventures into the why, proposing that the fine-tuning of physical constants, the precise balance allowing life to emerge, points toward intentional design. The Anthropic Principle finds an echo here, though interpreted not as multiverse statistics but as divine craftsmanship. Eastern philosophies offer a different lens. Hindu cosmology speaks of cyclical universes, expanding and collapsing in vast epochs called kalpas, each lasting billions of years. The Big Bang isn't a singular beginning but one breath in the endless rhythm of Brahma's exhalation and inhalation. This vision aligns intriguingly with some theoretical physics models, like Roger Penrose's conformal cyclic cosmology, where universes rebirth from the remnants of their predecessors. Similarly, Buddhist teachings emphasize impermanence and interdependence, framing the universe's birth as part of an endless chain of cause and effect, a cosmic-dependent origination that parallels quantum field theory's web of interactions. Indigenous cosmologies often blend the empirical and the sacred. The Maori creation myth of Ranginui's Sky Father and Papatuanuku Earth Mother portrays the universe as born from separation, a theme mirrored in the inflationary splitting of fundamental forces. The Aboriginal concept of the dream time, where ancestral beings shaped the world through song and movement, finds a poetic analogue in modern string theory's vibrating filaments. These narratives don't compete with science, they enrich it, offering metaphors that resonate with both the heart and the mind. Even within atheistic frameworks, the first second stirs profound philosophical inquiry. Existentialists like Sartre might see the universe's abrupt beginning as emblematic of life's inherent absurdity, a cosmic accident demanding we create our own meaning. Meanwhile, process philosophers like Whitehead interpret creation as an ongoing, dynamic event, where reality isn't a static object but a continuous becoming, a view that harmonizes with quantum physics' ever-fluctuating vacuum. What unites these perspectives is wonder. Whether through the language of equations, prayers, or metaphors, humanity reaches toward the same ineffable mystery. Why is there something rather than nothing? The dialogue between science and spirituality needn't be adversarial. When a theologian ponders the elegance of the Higgs mechanism or a physicist marvels at the cosmic order's beauty, they're speaking the same emotional language. The first second of the universe isn't just a puzzle to solve, it's an invitation to stand at the edge of the knowable and gaze into the sublime. One of the most stubborn myths about the Big Bang is the idea that it was an explosion in space, a cosmic fireball erupting outward into some pre-existing void. But here's the reality that flips this image on its head. The Big Bang wasn't an explosion in space, it was the explosive expansion of space itself. Picture a raisin embedded in a loaf of rising bread. As the dough expands, every raisin moves away from every other, not because they're exploding outward, but because the fabric between them is stretching. That's closer to what happened 13.8 billion years ago, except instead of bread, it was the fabric of reality swelling from a singularity smaller than an atom to cosmic proportions in fractions of a second. Another common mix-up is the notion that the Big Bang emerged from nothing. When physicists say the universe began from nothing, they don't mean empty space. They mean the absence of space, time, and physical laws as we know them. The nothing before the Big Bang wasn't a void waiting to be filled. It was a state where concepts like before and outside simply didn't apply. Imagine trying to ask what's north of the North Pole. The question itself loses meaning. This distinction matters because it transforms the Big Bang from a mere event into the origin of reality's framework. Then there's the misconception that we can pinpoint a single location where the Big Bang happened. In truth, it happened everywhere at once. The cosmic microwave background, the afterglow of the Big Bang, appears nearly uniform in all directions because every point in our observable universe was once compressed together in that initial singularity. When astronomers say the universe is expanding, they don't mean it's spreading outward from a central point like debris from a firework. They mean the entire cosmos is stretching, carrying galaxies along like dots on an inflating balloon. Perhaps the most poetic misunderstanding is the idea that the Big Bang was a chaotic, disordered event. Counterintuitively, it was remarkably precise. The temperature variations in the early universe, imprinted as those faint hotspots in the cosmic microwave background, differed by less than 1 part in 10,000. Without that near-perfect uniformity, gravity wouldn't have had the subtle density variations needed to sculpt galaxies. The Big Bang wasn't a random detonation. It was more like a symphony tuning up, with every quantum fluctuation playing a note that would later resonate into cosmic structure. Some even assume the Big Bang explains the universe's ultimate origin, but it doesn't. The theory describes how the universe evolved from an ultra-dense state, not what initiated that state or what, if anything, preceded it. When physicists discuss time zero, they're acknowledging the edge of our current understanding, not a definitive starting line. This humility is what makes cosmology so thrilling. The Big Bang isn't the final answer, but the gateway to deeper questions about multiverses, quantum gravity, and the nature of existence itself. Clearing up these myths isn't just about accuracy, it's about unlocking awe. When we replace the cartoon of an explosion with the reality of space-time unfurling, or swap nothingness for the suspension of physical laws, the true wonder of cosmic origins comes into focus. The Big Bang wasn't a bomb in the dark. It was the moment light, matter, and the very dimensions we inhabit flickered into being, a transformation so profound that its echoes still shape every atom in our bodies today. The next decade promises to be one of the most thrilling chapters in the history of cosmology, as cutting-edge missions and experiments prepare to probe the universe's first second with unprecedented precision. At the forefront is the James Webb Space Telescope, already revolutionizing our view of the early cosmos. Unlike Hubble, which peered back to within about 400 million years of the Big Bang, Webb's infrared eyes can detect galaxies forming just 200 million years post-Big Bang, closer than ever to that primordial first second. These ancient stellar nurseries act as cosmic time capsules, preserving clues about how the first structures emerged from those initial quantum fluctuations stretched by inflation. But Webb is just the opening act. The European Space Agency's Euclid mission, launched in 2023, is mapping billions of galaxies to trace dark matter's invisible scaffolding, a structure whose roots reach back to the universe's earliest instance. Meanwhile, on the ground, particle colliders are pushing energy frontiers to recreate conditions not seen since the first trillionth of a second. CERN Future Circular Collider, currently in the design phase, could smash protons at energies 7 times greater than the Large Hadron Collider, potentially producing particles that mediated the grand unification of forces. Imagine capturing a Higgs boson interacting with dark matter, or discovering supersymmetric particles that might have shaped cosmic inflation. These machines aren't just testing theories. They're effectively rebuilding the universe piece by piece in microscopic laboratories. But perhaps the most tantalizing prospects come from combining these approaches. The Simons Observatory in Chile and the upcoming CMB S4 project will scan the cosmic microwave background with such sensitivity that they could detect primordial gravitational waves, ripples in spacetime from inflation itself. If successful, it would be like hearing the echo of the Big Bang's first heartbeat. Meanwhile, neutrino observatories like DUNE and Hyper-Kamiok aim to catch these ghostly particles oscillating in ways that could finally explain why matter triumphed over antimatter. The boldest ideas extend beyond traditional astronomy. Projects like the Laser Interferometer Space Antenna LISA will float 3 spacecraft in perfect formation, using lasers to measure gravitational waves from merging supermassive black holes, events that could reveal secrets about the universe's first structures. There's even talk of quantum sensors that might one day detect relic particles frozen in time since the Planck Epoch. What makes this era extraordinary isn't just the technology, it's the potential for paradigm shifts. Every new instrument brings the possibility of discovering something that forces us to rewrite cosmology textbooks. Will we find evidence of cyclic universes, detect extra dimensions, or stumble upon phenomena we haven't even imagined yet? The first second of the universe holds countless stories waiting to be decoded, and the next generation of explorers, both human and robotic, are just beginning to turn the page. Mathematics isn't just a tool for cosmologists, it's the very fabric through which the universe reveals its deepest truths. When we trace the equations of general relativity backward to the Big Bang, or calculate how quantum fluctuations stretched into galaxies, we're not manipulating abstract symbols, we're deciphering the universe's native tongue. Take Einstein's field equations, those elegant lines of tensor calculus that describe how matter warps spacetime. In the first second, these same equations transform into a cosmic recipe book, telling us how an infinitely dense speck of energy could unfurl into the expanding cosmos we inhabit today. But here's the breathtaking part. These mathematical predictions, from the abundance of light elements to the exact temperature patterns in the cosmic microwave background, match observations with a precision that borders on the uncanny. It's as if the universe has been quietly solving its own equations for 13.8 billion years, waiting for us to catch up. Yet for all its power, mathematics walks a razor's edge between revelation and limitation. The same equations that flawlessly model the universe from 1 second onward crumble into infinities when pushed to time zero, a clear sign that our current math is missing something fundamental. This breakdown isn't failure, it's a cosmic breadcrumb trail pointing toward undiscovered physics. Some theorists believe resolving this requires new mathematical languages, perhaps loop quantum gravity's discrete spacetime calculus, or string theory's 10-dimensional geometry. Others argue we might need to rethink basic assumptions, like whether continuity and infinity are physical realities or just useful approximations. The irony is profound. The very mathematics that illuminates the cosmos also casts shadows where our understanding ends. What makes this dance between math and reality so fascinating are the surprises hidden in the numbers. When physicist Alan Guth first scribbled the equations for cosmic inflation on a notebook in 1979, he didn't just find a way to solve the horizon problem, he uncovered a mathematical inevitability. The numbers demanded that the early universe undergo exponential expansion, whether we liked it or not. Similarly, the Higgs boson's discovery in 2012 wasn't just a triumph of engineering. It was the moment a 50-year-old mathematical prediction materialized in a detector. These aren't lucky guesses, they're glimpses into a reality where mathematics seems to hold generative power, as if the universe is fundamentally a mathematical structure playing out all possible consistent variations. But can equations alone capture the visceral wonder of cosmic birth? A differential equation might describe how quarks condensed from plasma, but it can't convey the awe of realizing those same quarks now dance in your DNA. This tension between description and experience fuels ongoing debates. Do we discover mathematical truths about the universe, or invent frameworks that happen to fit? Some argue that mathematics is so unreasonably effective in cosmology because reality is at bottom mathematical. Others counter that we're simply filtering the cosmos through a human-invented lens, like mapping a sphere onto flat paper. The truth likely lies somewhere beyond this dichotomy, in a space where mathematics is both invented and discovered, a dialogue between mind and cosmos. Future breakthroughs may require mathematics we haven't yet imagined. Just as calculus was invented to describe motion and curvature, new branches of math could emerge to crack quantum gravity or dark energy. Some researchers explore category theory's abstract relationships, while others toy with non-commutative geometries where coordinates refuse to neatly multiply. There's even speculation that machine learning might uncover hidden mathematical patterns in cosmological data, patterns too complex for human intuition to spot. Whatever form it takes, one thing is certain: the story of the first second isn't written in words or images, but in the universal language of mathematics, a language we're still learning to speak fluently. As we stand on the precipice of new discoveries, equations remain our most powerful time machine, capable of transporting us back to the universe's very first heartbeat. From swirling galaxies in planetarium shows to psychedelic explosions in sci-fi films, the Big Bang has been depicted in countless ways, but how many of these artistic visions come close to scientific reality? Take the iconic opening sequence of 2001, A Space Odyssey, where a monolith triggers a star-filled explosion against Ligeti's haunting requiem. While visually stunning, it's more metaphorical than literal, a cosmic rebirth rather than a physics-accurate portrayal. In contrast, documentaries like Cosmos use supercomputer simulations to animate inflation's exponential expansion, with quantum fluctuations blooming into galactic webs. Yet even these rigorous attempts face a fundamental challenge. How do you illustrate a moment where time, space, and physical laws as we know them didn't yet exist? Artists often default to explosive imagery, fiery bursts radiating outward, but this misrepresents the Big Bang's core mechanic. Instead of an explosion in space, it was the rapid expansion of space itself. Some creators get inventive. The Tree of Life film's abstract sequence uses liquid light and microscopic photography to evoke primordial chaos, while Björk's Biophilia live concert visuals portrayed the universe's birth through pulsating organic forms, closer to the quantum foam's fluid dynamics. These approaches capture the feeling of creation rather than literal accuracy, leaning into art's strength, conveying awe where equations fall short. The most scientifically grounded interpretations often emerge from collaborations with cosmologists. The Powers of 10 short film, inspired by physicist Philip Morrison, zooms from a picnic blanket to the edge of the observable universe and back, scaling cosmic distances with mathematical precision. Similarly, the Big Bang AR app by CERN lets users witness quark-gluon plasma cooling into hadrons based on actual collider data. Yet even these projects take liberties simplifying timelines or amplifying visual drama, because raw science often lacks the narrative punch audiences expect. Abstract art might actually come closest to depicting the Planck Epoch's incomprehensible nature. Take Julie Meritou's large-scale canvases, where layered marks suggest chaotic energy coalescing into structure, an unintentional parallel to inflation's quantum fluctuations. Or Ryoji Ikuta's date-averse installations, converting particle physics datasets into strobes and soundscapes that feel like cosmic background radiation. These works don't explain the science, they translate it, using sensory overload to mimic the universe's overwhelming origins. The tension between accuracy and creativity raises deeper questions. Should art about the Big Bang educate or inspire? Must it choose? Perhaps the most powerful interpretations do both, like the fabric of the Cosmos VR experience, where users touch vibrating superstrings modeled on string theory equations. By letting viewers feel dimensions beyond perception, it bridges the gap between knowledge and wonder. After all, the first second wasn't just a physical event, it was the birth of possibility itself. Art that captures that magnitude, whether through equations or abstraction, doesn't just depict the cosmos, it continues its act of creation. If your curiosity about the universe's first second has been ignited, you're in luck. We live in a golden age of accessible cosmic knowledge. For those who want to journey deeper, Carl Sagan's classic Cosmos remains a masterpiece, blending poetic wonder with scientific rigor. The updated version, hosted by Neil deGrasse Tyson, brings stunning visuals and fresh discoveries, while Brian Greene's The Elegant Universe dives into string theory's mind-bending implications for the Big Bang. But books are just the beginning. Documentary series like How the Universe Works break down complex cosmology into digestible episodes, featuring interviews with leading physicists who study primordial gravitational waves and quantum fluctuations. Online learning platforms offer structured pathways for those craving academic depth. MIT OpenCourseware's Early Universe lectures deliver graduate-level insights for free, while Coursera's Origins of the Universe course translates cutting-edge research into interactive modules. For visual learners, PBS Spacetime's YouTube channel explores everything from inflation theory to dark matter, with animations that make abstract concepts tangible. And don't overlook podcasts. The Universe Today and Star Talk regularly tackle Big Bang mysteries, often with guest experts who worked on projects like the Planck satellite or the James Webb Space Telescope. Hands-on learners can experiment with simulations. The Universe Sandbox game lets you tweak gravitational constants to see how alternate universes might evolve, while NASA Eyes on the Solar System visualizes cosmic microwave background data in 3D. For real-time updates, follow arXiv.org, where physicists publish preprints on breakthroughs like primordial black hole detection or new inflation models before they hit textbooks. Local planetariums and university public lectures often host events on cosmic origins, blending live demonstrations with Q&A sessions. And if you're craving community, online forums like the Cosmology and Astrophysics subreddit foster discussions where enthusiasts and researchers decode papers or debate multiverse theories together. The universe's first second may be ancient history, but the tools to explore it have never been more at your fingertips, ready to transform wonder into understanding. Consider the atoms in your hands right now. The carbon in your skin, the iron in your blood, the calcium in your bones. Every one of those particles traces its lineage back to the universe's first second, forged in the crucible of the Big Bang and tempered in the hearts of ancient stars. You're not just living in the universe, you are the universe, a temporary constellation of atoms that once swirled in primordial plasma, now awake and wondering about its own origins. This realization isn't just scientific, it's transformative. When we grasp that our existence is stitched into the fabric of cosmic history, it reshapes how we see everything, from the air we breathe to the conflicts we wage. Think about the oxygen molecules entering your lungs with each breath. They were likely created in a supernova explosion billions of years ago, a violent death that scattered stardust across galaxies. The gold in your jewelry, neutron stars colliding in distant space, their unimaginable pressure fusing lighter elements into heavy metals. Even the device you're using to watch this, the silicon in its chips, the copper in its wires, was once part of interstellar gas clouds, cycling through generations of stars before finding its way into human hands. The universe didn't just create the conditions for life, it recycled itself into life, turning chaos into consciousness over 13.8 billion years of trial and error. This perspective dissolves the illusion of separation. The same quantum fluctuations that seeded galaxies also shaped the neural connections in your brain as you process these words. The hydrogen in your body's water molecules is older than the sun, older than Earth, a relic from the universe's first 3 minutes when protons fused in the fiery aftermath of creation. Suddenly, human history expands beyond pyramids and empires to encompass supernova and symmetry-breaking events, with our personal stories becoming brief but luminous chapters in a saga written in quarks and cosmic microwave background radiation. What does this mean for how we treat our planet? If Earth is a rare oasis where stardust learned to ponder its own existence, then climate change isn't just an environmental issue, it's cosmic vandalism. We're stewards of a pale blue dot that took billions of years to assemble the precise conditions for life, only for our species to alter its atmosphere in mere centuries. The ice caps melting, the forests burning, these aren't just local tragedies but interruptions in a delicate chain of events stretching back to the first second. When astronauts describe the overview effect, that profound shift in awareness upon seeing Earth from space, they're glimpsing what cosmologists see in equations, a fragile, interconnected miracle. Yet this view isn't meant to overwhelm, it's meant to empower. Recognizing our microscopic place in the cosmos doesn't diminish our significance, it redefines it. Every act of curiosity, every scientific discovery, every moment of awe under a starry sky is the universe's way of understanding itself. Your ability to marvel at cosmic origins is, in a very real sense, the universe becoming self-aware. That's why the study of the first second isn't just academic. It's an act of homecoming, a reminder that we belong to something vaster than our daily struggles. The same forces that birthed galaxies flow through your heartbeat, linking you to every supernova, every planet, every photon that's traveled since the dawn of time. So the next time you feel insignificant, remember, you're made of the rarest materials in the universe, shaped by the most precise physical constants, in the exact sliver of cosmic time where such complexity could emerge. The fact that you exist at all is a statistical impossibility, and yet here you are, a living testament to the universe's capacity for wonder. That's the true gift of cosmology, not just knowledge of the stars, but the realization that we are the stars, temporarily taking human form to ponder the mystery of our own existence. The first second of the universe wasn't just a fleeting moment, it was the ultimate cosmic domino effect, where every fraction of that blink set irreversible forces into motion. Picture a sculptor chiseling a masterpiece with a single, decisive strike, except here, the chisel was the laws of physics, and the marble was all of existence. From the Planck Epoch's unfathomable energies to the quark-gluon plasma's chaotic dance, each microsecond introduced new rules that still govern reality today. The universe didn't just emerge, it unfolded layer by layer, like a celestial origami transforming infinite density into galaxies, stars, and ultimately, the eyes reading these words. What's humbling is how fragile this chain of events was. Had the strong nuclear force been 2% weaker, protons might never have stabilized. If dark matter's gravitational pull had been slightly stronger, galaxies could have collapsed into black holes before life arose. Even the Higgs field's precise strength, giving particles just enough mass to form atoms, but not so much that chemistry became impossible, feels less like chance and more like cosmic craftsmanship. These aren't trivial details, they're the fine print in a contract that allowed complexity to exist. Yet for all we've pieced together, the first second remains a frontier. We've reconstructed the universe's infancy like paleontologists assembling a dinosaur from scattered bones, except our fossils are primordial gravitational waves, relic neutrinos, and the faint echoes of inflation. Every breakthrough, from the Higgs boson's detection to the James Webb Telescope's deep field images, adds another brushstroke to the portrait. But the canvas still holds secrets. What triggered inflation? Why does matter outweigh antimatter? Is our universe one of countless others in a vast multiverse? These questions aren't just academic, they're threads in a tapestry that connects quantum mechanics to the cosmos. The beauty of this quest lies in its duality. Science strips away myth yet replaces it with awe far more profound. The Big Bang wasn't a supernatural event, but understanding it requires concepts so bizarre, quantum foam, extra dimensions, false vacuums, that they stretch imagination itself. That tension between knowledge and wonder is where curiosity thrives. Whether you're an astrophysicist analyzing CMB data or someone gazing at the night sky, we're all participants in the same grand investigation. As this chapter closes, remember, you're not just learning about the first second, you're experiencing its consequences. The same quantum ripples that seeded galaxies also shaped the neurons firing in your brain right now. The universe didn't just create the stage for life, it engineered the conditions for life to understand its origins. That's the real magic, not just that we're made of stardust, but that stardust can contemplate its own existence. So keep questioning, keep exploring, and most of all, stay amazed. The cosmos has been writing its story for 13.8 billion years, and we've only just